Welcome to lecture 22. Today is 8th. So let us continue our discussion with pulse amplitude modulation. Now we can visualize pulse amplitude modulation in two ways. One way is the obvious way, that is we are partitioning the time axis. So where say t is the symbol interval, so symbol time period we can say. So for every symbol time period we are sending one symbol at a time. So how that one symbol will be placed? It will be placed by using the pulse amplitude modulation. So we can write that xt for the kth interval, we can say. So I can write that in a third bracket. This is equal to essentially the value xk in the kth time interval multiplied by the basis function. So basis I am writing to be p, pt minus kt suppose. So this is true for when t is within kt and k plus 1t. Okay. Why I am writing p? Because that will be obvious when we will discuss. This is in the last class I wrote it to be the phi. So this is basically the basis function. So this is one dimensional signaling. So this is the basis function, the shifted basis function. Okay. So this is one way of writing it. Another way is essentially talking about the entire timeline. So without partitioning. So then what we have to do? We have to basically add these things because these are all defined over this interval. So if we simply add them, we will get the entire equation. So we will get like add these equations for different k's. So k for all integers. So add all these equations. So that is basically xt, which I can write as summation of xt over that kth interval, and k is equal to minus infinity to infinity. So which is essentially equal to xk. This is the discrete time signal, isn't it? That is the like after the map. So from the bit stream you are mapping to xk in the kth time interval, pt minus kt. K is equal to minus infinity to infinity. So I can visualize like this. Now this equation is basically convolution equation, isn't it? So you can think of that. Okay, so p, if p is the impulse response of a filter, so impulse response of a filter then I can think xt to be basically the input is coming to be the sequence, which I can write as simply xk, or I can write in terms of the impulses, say xk delta t, t minus kt basically. So I can write like that as well, k is equal to minus infinity to infinity, which is basically those symbols, those values are coming. So whatever be xk value at different interval, at different time instances, and you are passing it through the filter with impulse response pt, then the output will be this xt, isn't it? So you can think in this way as well. So it will be good if we so of course when I am writing just for one time interval, this is one dimensional signaling where you are using only one basis function. However, when I am observing this convolution equation, or you can think that okay, if I take this p t minus kt for all k to be a set of basis functions where the shifted form of p generates that basis set, infinite basis set, then this entire sequence, which is an infinite sequence, that will work as the coordinate. So in that sense also we can think of this equation, and then this is the like basically the Fourier synthesis equation, and you can generate the analysis equation by the inverse Fourier transform. So essentially if they are the orthonormal basis function, then you can basically take the inner product of xt with them to get xk back. So that is obviously possible. However, I don't know yet whether they are orthonormal basis function set or not, the shifted versions, whether this so I don't know yet if p t minus kt for all k like generate this set generates an orthonormal basis set. Set or not. If it generates, then the life is easy because this equation itself will be a Fourier synthesis equation. But if like this inner product works, then life is really easy because then I can generate xk to be simply like the inner product of xt with p t minus kt, and that will give me the value. And even if this xt, what is received at the receiver side, is noisy, suppose xt is not exactly like whatever is received is after the baseband channel. So suppose you have xt which is sending to the baseband channel, equivalent baseband channel, and what you are getting. So we are assuming that the baseband channel does not introduce any distortion, even any delay. Delay does not matter because delay will basically, I can shift the entire thing if the timing can be transmitted reliably. I can take care of delay. Delay is not an issue. But distortion, we have to do equalization, and I hope you have done that in analog communication. Anyway, one thing which will be there, which will be there is the noise. We cannot help but have some noise here. So whatever you are receiving here, suppose x hat t, that will be basically xt plus some noise process zt. This noise process typically is additive white Gaussian noise. So now if you just pass it through some filter, which is basically computing this inner product, then some filter, then what you will get, and this is linear, of course, this is a linear filter, some linear filter, then this xt will give you back xk, no problem. But additionally, you will have the inner product of zt with the corresponding pt minus kt. So this inner product you will have additionally, which pt minus kt, and that will give you, clearly that will give you one random variable. So that random variable we have to characterize, and we will do that exactly in the during detection theory. Okay, so it will give you some additional randomness, this is a random variable definitely, but this another random variable which is coming from the noise, that will basically like create problem in the detection process. So here we have to do the detection after getting the random variable. Okay, but before going there, let us first try to understand whether we can take this or not, and if it is not, then from this equation how can we do detection, how can we do demodulation. So we will talk about demodulation. Clearly this choice of the PAM alphabet, the pulse amplitude modulation alphabet, that alphabet is like decoupled from the choice of the basis function. Basis function basically talks about signaling and the ease of demodulation. It basically works on that line, and the choice of the alphabet basically works with the optimization of energy and then bit rate, and in the last class we have shown you, right? So those optimizations it talks about. There is another thing which we'll introduce today, which is called the inter-symbol interference. So inter-symbol interference. So this is one problem which is essentially a signaling problem. So even if there is no noise, this is possible. And why this is possible? Because our channel is strictly like baseband, band limited channel. So since our channel is baseband, band limited channel, and this is kind of strict. This is something which you are obtaining from the like provider or service provider, so you cannot really have access to the other band, and that means you cannot have truly some signal, like the signaling cannot be restricted within the specified time window, so the signal will spill out. So whatever signaling you are like assigning, that will spill out. So this P will not be restricted within one time interval. So that's why what P to design such that even if it gets some spilling, there is no interference between the symbols. So inter-symbol interference is basically that thing that when you have the time windows, so this is 0, this is t, this is 2t, and you expect your symbol, the representative signal corresponding to your symbol will reside within this, and there will be no overlap with the other one, but that is not the case. It will be like having some overlap. Why? Because of that uncertainty principle, obviously. So when digital communication actually started, think about the telegraphy era in 19th century, like people thought that sending 1 and 0 through a telegraph channel, so like copper wire channel, so why should we have some analog signaling? Let us have some DC signaling, DC kind of signaling, which is basically rectangular wave kind of signaling. So they thought that okay, let us keep PT to be just the rectangular pulse. So it is basically 1 when t is between 0 to t and 0 otherwise. If so, if it is clearly rectangular, then how does it look like? How does the waveform look like? The waveform will look like suppose the values are the alphabet is say -5, -3, -1, +1, +3, +5. Suppose there are 6 symbols in the alphabet, and you are getting in different intervals, you are getting different values. Okay, so this is your PT. So the signaling will be like this. Suppose this is 3, this is 1, this is -3, this is -5, this is +5, this is +3, this is -3, -5, etc., etc. So this kind of staircase kind of signaling, and this is a time domain signal. So clearly this signaling does not have any inter-symbol interference because your signal is entirely within that specified interval. There is absolutely no spillover, and you can clearly detect it just by sampling. Like even a simple threshold will work, but sampling is fine. So at any point within that 0 to t, like any interval kt to k plus 1t, you just sample, you will get the value. But what is the problem? The problem is the bandwidth. So if you take this kind of waveform, the rectangular waveform, what is the Fourier transform? It is sin c. So the bandwidth of these kind of waveform is no way band limited. So when initially they thought about it, they did not really think about that the bandwidth will be the most important resource in designing communication system. But nowadays, whenever you are thinking of some wireless communication system or some optical fiber communication system, the main thing is basically the bandwidth. So you cannot have this kind of discontinuous signaling, the square wave kind of signaling. It is impossible. So we need a better kind of PT. The other extreme of PT is obviously the sin C. So sin C we know is a very nice waveform because it is exactly band limited. But is there any inter-symbol interference? We have to think, because inter-symbol interference will occur if there is some like error introduced by the neighboring signal. So let us observe very naively. We are not bothering about other issues as of now, but suppose you are taking PT to be a sine-seq waveform. So sine-seq waveform, we know that it does not have any problem of bandwidth. So it is exactly because its Fourier transform is rectangle. So that is entirely baseband. So for sine ct by t, the Fourier transform will be limited to, this is the Fourier transform, between minus 1 by 2t to 1 by 2t, and this is height is say capital T. This is the Fourier transform of sine ct. So which I can write to be a t rectangular ft. We can write like that. So the bandwidth problem is not there. What about the waveform generation problem? So waveform generation problem will be, suppose this is plus 3. So at this interval you are generating a sine C curve which is so something like that, and its length height is 3. In the next instance you have a sine C curve whose height is 1. So next instance is basically this one. This is the next instant. So you will have something which is 1. My drawing is not that good here, but anyway you can understand. So you have these pulses. In the next interval it will be minus 3. So here you will have a minus 3. And what you have to do, you have to basically add all of them together. So all the pulses you have to add, which will give you the final waveform, and that you are sending. So we know that when this pulse is assuming the value 3, all the other pulses have a 0 over there. So really speaking, there is no interference. As long as you can recover the clock exactly, you can do the sampling exactly. But if you cannot do, there is some error, then it will be problematic. That is not the only issue. There are more issues, because one issue is that the sine C is not a causal filter. So because this goes from minus infinity to infinity, so you have to wait for the entirety to get even one sine C. So this is not a causal filter. So to get a real causal filter, what you have to do, you have to basically truncate it. So you cannot really realize exact low pass filter. There will be some roll off, right? Now that is one problem, of course. So you have to truncate it. That is obviously there. Another problem is that how fast this particular like time waveform is decaying. So one particular PT, which is defined over one time interval, and it is definitely spilling over outside, but how fast it is dying down, how fast it is decaying, it is only at 1 by small t. That is the rate by which it is decaying. So that is not good enough. We want faster decay of the waveform. So sine C is not a good choice. We want something better. Okay. So what are the conditions, what are the goodness of waveform, the PT waveform which we want to have? So we can list it basically. So PT should have the following qualities. Yeah, I know you are thinking that we learned about Prolet spheroidal wave function, why not yet? Now this is a little anachronism. So I discussed Prolet spheroidal wave function, but that was a discovery in the 1960s, like in the true sense. And what I am teaching now, the design of PT and like intersymbol interference, it is 1920s. It is like 40 years earlier. So it was done by Harry Nyquist. So that time Prolet spheroidal wave function was not there. But even when today, even now we have the Prolet spheroidal wave function. But the problem with Prolet spheroidal wave function is that the circuitry. So designing, generating those waveforms using a simple, say, Butterworth or Chebyshev filter is not possible. So we need huge amount of circuitry. But I don't really want to go there, because Harry Nyquist gave us some method by which, even without restricting it entirely within that time window and the band which the Prolet spheroidal wave function does, we can do a better job. We can do a like good enough job, as long as the corresponding condition, which is the Nyquist criteria, that is satisfied. So that is what we want to discuss today. So this PT, this waveform should have the following qualities. One is, of course, PT has to be causal. The filter has to be causal. Okay, fine. I'm not restricting that PT will be 0 for all t less than 0. Rather, I'm allowing some delay. So a little delay is allowed. Fine. So I can mathematically write that to be that PT is equal to 0 when t is less than some minus tau, and tau is a positive number which is finite. So tau is a finite number. So sin C is not allowed, definitely. Second is, of course, this has to be like support limited, or PT has to be band limited. So this should be limited, baseband limited to some like bandwidth, say BB. So this is the baseband bandwidth, and which will be a little greater than 1 by 2t, which I am naming to be WB. These things we will discuss next. So this WB is called the nominal bandwidth, where capital T is the symbol time, symbol duration, and this BB is the bandwidth of the signal. Of PT. Now this bandwidth definition is not 3 dB bandwidth, it is exact bandwidth. Exact bandwidth means that PF will be 0 for F greater than BB. Like it will be 0. However, this BB should not be too bigger compared to WB. If so, like this is some useful resource. I don't want BB to be hugely large. Suppose you have some very large BB and your WB is suppose here. So this entire area is basically getting wasted. So what you can do, you can then increase WB like as close as possible to BB. There will be some requirement which will show. So if we can increase WB, what that will do, that will basically decrease D, and decrease D means you can increase the bit rate. So as time period decreases, you can basically send the same amount of bits in a less amount of time, so that increases bit rate. So that is a useful like objective which will be satisfied. So we really do not want this BB to be very large compared to WB. It will be close. So that condition we will develop today. Last but not the least, so this is the first. So you can see that one is time, one is frequency, and third is ease of demodulation. Basically this is the circuitry. So my objective is that like signal, the symbol should be obtained easily. So this is one objective. Now let us see that how we can connect these dots. What we can do from the like characteristics of Fourier transform. One thing we know that if one domain, suppose you have some PT, so this is your time window 0 to t for PT, and its corresponding spectrum is say 0 to BB and minus BB. This is the spectrum. We know that if this is the decay is faster, decay is sharper, then it will be slow, and if this is slow, then this will be faster. What I want to do, like have both PT to decay really fast, like as much as we can. So that challenge we have to handle, and we have to basically ensure that there is no intersymbol interference. So obtained easily without any ISI, any intersymbol interference. Right now, for the time being, assume no noise, because noise will be analyzed separately later on based on these filters. Okay. So good enough decay we want to have. So we start with the third point, which is the easy demodulation part. So let us talk about demodulation of PA. So we are getting our motivation from the understanding of sampling. So when I have drawn a signaling like the rectangular or the sine C, we see one thing for sure, that is to get back the digital like discrete time signal, the symbol, you have to do sampling, because this is essentially sampling, uniform sampling. Okay. So for this, the sampling can be anywhere between that kt and k plus 1t. For sine C, it has to be exact. So sampling block will be there. So let us draw the diagram. I am drawing the entire diagram. So this is the bit stream coming. So you have the constellation map first. Which maps to the symbols. So which I can write as xk at kth time unit. And then you have the digital modulator, which is essentially the filter PT. This is basically the filter PT, and it gives you xt. Now you have the baseband channel, which gives you x hat t, and if there is no distortion, no noise, then this will be equal to xt, isn't it? Then I will have my demodulator. So I expect that the demodulator will be one block, which will be possibly linear block, because linear is something which we can do. So we are starting with linear block. If it is not possible, we can think then we have to go to some non-linearity and out. But if it is possible with linear block, it's fine. Followed by a sampler, and that sampler will be working at time kt. Yeah, I understand that from here to here there will be some delay, and that corresponding information is provided there. So we can compensate that. Okay. The entire thing will be delayed a little bit. That's fine. So that will give me this back. So xk will be coming here. And then by the inverse map, we can get back the bit stream. So this is the inverse map, we can say. Now this inverse map will not be so easy when there will be noise. So then this block will be called the detection block. So we will be talking about that later on. But for the time being, let us look at this block, which is the demodulation block. So this entire block we can talk about the digital demodulator. Digital demodulation. Okay. So linear block means there is some impulse response that is like a filter. Okay. Input is xt is coming, and suppose you have some filter whose impulse response is qt, and you are getting it, then you are sampling it at time kt. You are expecting that you will get xk back. Okay. So suppose this is some rt. So what you are getting is basically rkt. So I want that rkt will be equal to xk. So what is rt? Rt is xt convolution qt. So I can write that as minus infinity to infinity x tau qt minus tau d tau. That's rt. So from here you can clearly see that if one choice of P and Q can be like, if P is rectangular, then this Q is not even required, so only sampling will work. Okay, if P is the PT is sin C, cardinal sign, then also this can be a rectangular block, like multiplied by unity followed by a sampler, it will work. We are trying to generalize it. So let us put the equation of x tau. So what is x tau? Going to the next page. So xt is equal to summation xk p t minus kt, k is equal to minus infinity to infinity. So put it there. So your RT will be integral minus infinity to infinity summation k is equal to minus infinity to infinity xk p tau minus kt, this into qt minus tau d tau. Now what I will do, I will apply Fubini's theorem. So I will like swap the sum and the integral, assuming that is permitted. So the kind of signal we will do, that will be strictly L2. So P convolution Q, that will be strictly L2, then this is permitted. Okay, we are working in that Hilbert space setting only, not generalized space, then things are problematic. So if I do this, you can see that this integral will have only d tau, so there is no k. So I can take the xk outside, and what will be inside the integral? It will be p tau minus kt q t minus tau d tau. So it is basically convolution between p and q, and that result is delayed by kt. So I can write this as summation xk some g t minus kt. I can write like this for k is equal to minus infinity to infinity, and where this g t is essentially this p tau qt minus tau d tau. This is not surprising because these blocks, this baseband channel is doing nothing. It is just a multiplication of one unity. So these blocks pt and qt, they are in series, they are in cascade, isn't it? So cascaded means ultimately they will be convolved. So pt and qt are convolved to get gt. In the frequency domain, the corresponding transfer functions are multiplied. That is what cascade do. So this is the convolution of p and q. Now from this RT, so what is RKT? So RKT is basically xk g. Okay, I am putting it to be some m or something. So xm, m is equal to minus infinity to infinity, and g k minus m t. Okay, that is what RKT is. So RKT will be equal to xk only when g0 will be 1. So RKT, you observe what is happening. So RKT will be xk if and only if g0 is 1 and g all other kt will be 0 for k not equal to 0 and for all other k. If this is satisfied, if this condition is satisfied, then only you will get RKT will be equal to xk. That xk will come only when m is equal to k, and that g0 is 1. This is a discrete sum but infinite. Only that xk value will be chosen only if this is satisfied. So this is interesting. This particular condition is called the Nyquist condition or Nyquist criteria. or we'll say that like signal GT, which is basically the convolution of PT and QT, the modulator filter like impulse response, and the demodulator impulse response, the convolution of the both, that is GT. So we'll say that GT is, if this is satisfied, then we'll say that GT is ideal Nyquist. Okay, so far so good. So example of GT, obviously sin C is one example, so that already known. So ideal Nyquist. Ideal Nyquist will be Z0 or 0t, I can write, is 1, and GKT is 0 for all other k. Okay. So example, one is rectangular. So this is say 0, this is minus t by 2 to t by 2, or 0, I can take 0 to t also, no issue. You can see that at every other t to t minus t, everywhere this is 0. At 0 it is 1. So this impulse, this rectangular pulse is ideal Nyquist, no issue. Sin C is also ideal Nyquist. 0 minus t, 2t minus 2t. So why? Because sin C is like that. You see, all the zeros are basically all the integer multiple of the time period capital T. So except 0, where it is 1, everywhere else it is 0. So that is also ideal Nyquist. So there can be infinitely many such ideal Nyquist waveform. And these two are the trivial examples which we are doing like from the very beginning. Ideal Nyquist waveforms. But which one to choose? And what is the criteria of choice? Like how to generalize the like way of choosing the ideal Nyquist waveform? Is there any structure, frequency domain structure? So let us see that. These two are not possible. We will not work with them. We are not happy with them. So the problem of this is it is having it is not band limited. We want something which is band limited. This is not band limited. And this is like slow decay, not causal. These are the issues. So we want something better. So let us now develop the frequency domain Nyquist criteria which will generate the ideal Nyquist waveform. Okay. So let us talk about the Nyquist criteria. Next. So suppose you have your like GKT signal which is arriving at some ideal low pass filter. This is suppose ideal low pass filter. Okay, and this the bandwidth is minus WB to WB. So what is WB? WB is 1 by 2t. Okay. So what is the impulse response? So if the impulse response is say HT, it is essentially sin C. The height is say capital T. So the spectrum is basically T rect. So this is T by T. the corresponding spectrum, I can write it as F to be T rect TF, or yeah. So suppose this is coming, and this is the impulse, this is the ideal filter. Okay, so what will be the output? So output, this is the impulse train is coming, so I can write this as into delta t minus kt. This is what is coming. Okay, so output will be obviously gkt sin c t by t minus k. This is what is output. Okay, now what if G is ideal Nyquist? So in this setup, this is some hypothetical setup. This is the genius of Harry Nyquist. So Harry Nyquist presented this novel idea that suppose I have the sample values of the waveform GT, and let us now pass it through the ideal low pass filter, and you are getting some waveform, some nice waveform. Write it as ST. Okay. So what is ST? If GT is ideal Nyquist, so if GT is ideal Nyquist, then G0 is equal to 1 and all other at 0 for all other k. So in this entire sum, only one term will survive, that is Z0, which is 1, and the corresponding sin c term will be sin c t by t. So ST is nothing but sin c t by t. So what you are getting, the output is basically the impulse response of the filter. That is what you are getting. So you have a nice equation, that is at one side you are this, and another side it is only sin ct. Take Fourier transform of this as well as this. So you have the equation. So if it is like ideal Nyquist, then you have the corresponding equation, that summation gkt sin c t by t minus k is equal to sin c t by t. Now you apply Fourier transform on this. If you apply, what you get? This is essentially the aliasing theorem. So you will get summation. So this is the impulse train. What is the spectrum of that? It is basically the spectrum of GT, that is G hat F, and that is replicated at the interval of 1 by t, isn't it? So you will get the corresponding spectrum will be G hat F plus m by t, that is 1 by t is the period, and this will be basically the convolution of this with sin c, that is basically rectangular. So rectangular of ft, isn't it? So that will be equal to, this side is t rectangular ft, and this is for all m is equal to minus infinity to infinity. So that is the spectrum of the condition, and this particular condition, this particular equation is called the this particular form is actually not exactly this, but limit in mean square. This is a Fourier integral, Fourier series. So the convergence of this to this will be in terms of L2 convergence. Okay, that we have to understand. I am not elaborating on that at this point of time. It's fine. So this particular thing, if you are confused about how from here you are getting this you just like refresh your signals and systems background. This is called the aliasing theorem. Sampling aliasing, you must have already read it. Go back. Now I will use I'll characterize the frequency domain characterization of the Nyquist criteria will do, which is called the band edge symmetry, and that will basically help us in generating the PT, basically GT, which is PT convolution QT. So we'll get some band edge symmetry of the spectrum. Okay, to go there, so we already developed a few notions like the WB, which is the nominal bandwidth, which is 1/2T, and BB is the bandwidth of the signal, and I'm assuming BB is the basically the bandwidth of the entire signal GT. Okay, not only P, or you can think that P and Q are having the same bandwidth. So this is the bandwidth of GT. Okay, so what we are choosing now, why I am saying that BB has to be greater than WB. Suppose you choose BB to be less than WB, suppose, then what will happen? Then this is a trivial scenario. So this is the spectrum, suppose the spectrum I am drawing. So this is 0, this is WB, this is minus WB, and this is say 2WB, etc. So suppose BB is less than that. So this is your BB. So your G spectrum, suppose this is your G spectrum, G hat F. Okay. So G hat F is within this. Then the equation, what is written over there, this rectangular will enforce everything within that minus WB to WB. So everything will be within that minus WB to WB, and these different G hats for different M, that will be replicated at the interval of 1/2. So it will be replicated next around this. But since this is within that WB length, so from here the WB length is up to WB, so there will be no overlap, so there will be no aliasing at all. So in this condition, no aliasing, and this is exactly what is used in sampling, isn't it? So no aliasing is possible, and if there is no aliasing, so in this sum you have only one term of M, which is M is equal to 0. Put M is equal to 0, so what will you get? You will get basically G hat F. Oh, there will be one T, right? Yeah, T will cancel out basically, so there will be a T here as well, so that T will cancel out. So from here you will get only G hat F, rectangular is 1, is equal to 1. So you will get G hat F, will you get rectangle, okay, Ft. So what is that? That will give you GT is equal to sin C. Do I need that? I don't, because that we have already left behind. Yeah, that factor 1/T or something. Okay, so this is not something which we desire. So no aliasing is not the choice, not the right choice. We want aliasing. Aliasing will help us here. So no aliasing is not the right choice. We will take help of aliasing. So aliasing is desirable. So this is a nice question that give me one situation where aliasing is desirable. You want aliasing. So we will take aliasing. Okay. So my BB is definitely greater than WB. However, I don't want BB to be very greater than WB. So I am restricting it within WB and 2WB. So I am restricting BB to be here. So what is happening? if this argument we have already given, that if the BB is very greater than, then you are basically wasting your bit rate. You can increase it. So this is your 0, this is a WB, this is a 2WB, you have your BB somewhere here, okay, closer to WB. Then you have overlap. So your spectrum is, suppose, this, something like that, okay. This is the spectrum of GF. Let us take GF to be real and even, okay. So we let us have some nice symmetry. So if GT is real and even, then we know the corresponding Fourier transform G hat F is also real and even. There is a nice symmetry. Now what is GF G hat F minus 1 by T? So that will be basically around this 2WB. So it will have something like that. Okay. So within that interval of 0 and WB, because that is where the rectangle is, the rectangle pulse is defined over there only. So how many maximum overlap we can get? Only one, because the next one, which is around 3, that will have overlap with this pulse but not with the first one. So if I just restrict our observation to 0 to WB, there will be at most 2 overlaps. So this ensures that there will be at most 2 overlaps. So we will choose, in that sum, we will choose only 2 values. One is m is equal to 0 and another is m is equal to minus 1. Those 2 values will give me the equation. That is understandable, isn't it, from this? So let us write that down. I am missing some this, okay, it's 9. So what we can do, we can now write down this equation with 2 values, m is equal to 0 and m is equal to minus 1. So you will get G hat F plus G hat F minus 1 by T is basically 2WB is equal to 7. Okay, so this is the equation, and this equation is written for F is between WB and 0. In the positive side I am doing the exact same, will be working for the negative side as well. So I am working in the positive, it is having the symmetry, so no issue. Now since G is real and even, so we can write this to be G dash F minus 2WB to be equal to G hat 2WB minus F. That is the symmetry. This is like conjugate, but conjugate is real because like this thing is real, so conjugate is same. So I can write it as G hat F to be plus G hat 2WB minus F is equal to 1. Why I am writing in this way, let me tell you. So the next step I'll do a little substitution, that is F minus WB is equal to, say, delta. Okay, so if I put that, then it will be G hat WB plus delta plus G hat WB minus delta is equal to 1. Or I can write G hat WB plus delta will be equal to 1 minus, or minus delta equal to 1 minus G hat WB plus delta. Okay, this equation is extremely important because this will give us some strong geometric understanding of the spectrum. So suppose this is 0, this is WB, and this is a BB, and I have my form which is say like this, like this. This is my plot of G hat F. So you see delta is basically the deviation from WB. So F minus WB is delta. So delta is positive this side, delta is negative this side. Okay, this is the positive side. So WB minus delta is basically for say positive delta is basically this side. So that value, this value is essentially 1 minus this value. What does that mean? 1 is say this one, this is 1. So what does that mean? That means this one is equal to this one, and as you move along, as you move delta from here to here, what you are doing, you are basically seeing that around this WB, whatever part is here, that part is having exact symmetry. This part is having exact symmetry with this negative void. So whatever is there. So it is like some spectral budget. You can see that there is some rectangular spectral budget. That budget you are allocating in such a way such that there is a rotational symmetry here. So you can basically rotate this block and it will fill this area. If you rotate 180 degree, it will fill this negative area, and that will give you the entire budget. And that is what it is. This side is rectangle, right? I should have written 1 is rectangle for this. Yeah. So this is called the band edge symmetry. So for this scenario, that this part should be exactly like this, and this will be our governing equation. So that will give us the choice by which we can design our filter. So I think I should stop today. One filter which is used, which has this band edge symmetry, is called the raised cosine filter. You can search about it. So it is having a like transfer function which is having a nice roll-off, and its corresponding like time domain, the inverse Fourier transform, which is the impulse response basically, that decays at around 1 by t cube, which is much faster compared to the 1 by t of sin c. Of course it is not, this is strictly band limited, as you can see, to BB. It is not exactly time limited, but the roll-off is too fast. 1 by t cube is too fast. So that serves our purpose, and this is exact Nyquist, so ideal Nyquist, so there is no intersymbol interference. Okay, go and search about this. In the next class I will be talking a little bit, but however I will not be going to derive the entire raised cosine or like implement the raised cosine using some polynomial. That will be beyond the scope. But if you have done like filter, which probably I have taught you, right, Butterworth, Sevisev, etc. So similarly, like how to design this filter, you can have a look in that book. And if somebody of you are interested in designing this, you can contact me separately. We can talk about that. Okay. So with this I'm stopping. In the next class we'll be talking that how this PT, which are Nyquist, which satisfies the Nyquist criteria, how that can generate like infinite set of basis functions, such that the first thing which we are told that we want to have this as a Fourier expansion, such that like automatically this inner product will give us the solution. So that we will talk, and that is called matched filter. So it will be understandable. Yeah, once that is done, then we can move towards the complex valued signaling, which is the quadrature amplitude modulation. Okay, so till then, bye.